In this lecture, we will continue discussing the properties of light. Properties of light. Okay, so the first thing we should know about light is that it has a speed. So here's the speed of light. All right, it's c is equal to 792.458 meters per second, right? Or for short, it's equal to 3 times 10 to the 8 meters per second, right? Okay. Now, because of that, the speed of light imposes a time delay. That time delay can be significant, all right? So back in the bad old days, before they invented fiber optics, they laid fiber optics under the oceans. The way you talk to people in other countries was through telecommunication satellites, right? And so if you had a telecommunication satellite, right? And the satellite is basically sitting about 400,000 kilometers right above surface of Earth. There's a reason for this, actually, it turns out. If you're sitting about 400,000 kilometers above the surface of the Earth, at that orbit, your orbit is basically once every 24 hours, which means that to someone on Earth, you look like you're a fixed point in the sky, right? And so you can aim satellite dishes at it and stuff like that, right? So in this case, basically the time delay, you see, basically it goes from here, goes up to the satellite, comes back down again, right? You can imagine this distance here is d. This is like the surface of the Earth, say, right? Okay. And in that case, you can imagine that delta t is equal to d over c. It's actually 2d over c because I can go up and come back down, right? So that's about 80,000 kilometers divided by 3 times 10 to the 8 meters per second, right? And that roughly turns out to be about 3 times 10 to the minus 1 seconds, or 0.3 seconds, right? So if you're talking to someone on the phone, you might say something, and then it will take 0.3 seconds to reach them. They'll start responding, take 0.3 seconds to talk back, and so it's about a 0.6 second delay before you hear a response, right? Okay, and so basically back in the day, basically when you were talking to someone on the phone, long distance, right, across countries, you could definitely tell that this was a major effect. All right, so let's keep talking about properties of light. Let's talk about the propagation of light. Okay. And there are two ways of thinking about this. That's not propagation. Let me write this right. It's correct. Propagation of light. Good. Okay, got that right. Okay. So you already know how light propagates, right? So light is described by the wave equation. Okay? And so in principle, if you solve the wave equation, you can just tell everything about how light propagates, right? Now, that wave equation for a lot of different, if you have a lot of different pieces of light, it starts to get hard to do, right? So there are two ways to describe it without the wave equation. So two ways to describe light without wave equation. So let me talk about the two ways now. Right? The first one is called the Huygens construction. Okay, let's talk about what Huygens construction is, right? So I'll describe it first, and I'll just basically illustrate this, right? So what you want to do is you want to think about each point on the wave front, right? Forms small spherical waves, okay? And then basically the next wavefront is due to the sum of all these spherical waves. Okay, so let's talk about how that works, right? So imagine you have a wavefront like this, okay? And now what you want to think about is that imagine that every point in the wavefront basically starts giving out those spherical waves, right? Every single point, okay? Okay, so if you draw that out, what that looks like. Now these waves will start to propagate outward, and they'll interfere with each other in such a way that some of the things will add up, some of the things will subtract from each other, and the sum of it produces a second wavefront. Okay, so this is a secondary wavefront. And that's how light propagates, right? So we imagine like a long wavefront, you have a bunch of these spherical waves being emitted, these spherical waves go out, they start interfering with each other, like basically immediately, and that basically generates a second wavefront, and this in turn also basically sources new spherical waves which propagate outward as well. So that's a Huygens construction, right? Okay. Now the other way of doing it, okay, is what they call Fermat's principle. Okay. So this is basically light takes the path that minimizes time. Okay, and so this is also called the principle of least time. Okay, right. This one's not obviously why it works yet. Well, not to you at least. But this is an extremely powerful statement. All right, you'll see why in just a second. Right. So let's talk about reflection and refraction. Okay. So, and I think, let me think, what should I talk about first? Let's see what I do here. All right. So the first thing I'll say is that light moves at c, which is the speed of light. Okay. Now this speed of light c is just a number, so that's 3 times 10 to the 8 meters per second. So light moves at c only in a vacuum. Okay. In all the materials, it moves at v less than c. Okay. All right. So what we can do is we define n, right, is equal to c over v, which is the speed of light in vacuum over speed of light in material, right? The material could be like any transparent material will work, glass, air, water, okay? Define this one as n as the index of refraction, right? And this index of refraction just depends on the material, right? So glass has an index of refraction, air has an index of refraction as well, right? So let's talk about the material and n in both cases, right? So I'm going to list a few materials. There's air, there's water, right? All the transparent materials. There's glass, and my best friend is diamond. Right? I wish it was my best friend. It's not. Air has index of reflection, which is 1.003. So you can see this is the speed of light in air versus the speed of light. So the speed of light is ever so slightly smaller, right? It's nearly the speed of light, but it's ever so slightly smaller, right? For all practical purposes, air and vacuum are essentially the same. Water is basically someplace where you start getting something different. That's 1.32. Glass is 1.5 to 1.66. If you ever go to eyeglasses and try to get plastic lenses and stuff like that, those say high index eyeglasses, that's 1.67. Really high index is 1.71, all right? And there's also super high index as well, right? So they get higher and higher index. But the best, if you can make glasses out of diamonds, 2.4. It's the highest index refraction material we have on Earth. Okay. So this is very interesting, all right? So now let's basically consider the following, okay? All right, let's just think about what I want to say here. Right. Consider light incident, that means falling on a material. Really two materials. So let's think of this. So let's imagine this material 1, material 2, okay? There's some light here, comes in. And it comes in with some angle relative to normal, theta, okay? Now, there's going to be a few things that will happen, right? So first of all, some light might be reflected back, okay? This is reflected light. And some light will be basically refracted into this thing. Let's see what I want to say here. Okay, theta double prime, say. Okay, sorry. This is I'll read it right again. Theta double prime. Okay, just make it really clear. Right, so this is the reflected light. This is the transmitted, or what I call refracted light. Oops. Refracted All right. And this here, angle of incidence this is the angle of reflection, and this is the angle of refraction. Okay, so those are the three angles basically. Right, so there's an instant angle in, reflected light, and then angle of refraction. Okay. Now, it turns out that you can use Fermat's principle to get all the results here, basically, right? Okay. So, for instance, right, if you're going from this point to this point here, all right, and you want to pick the point of least time with the constraint that hits the surface somewhere, the principle of least time actually gives you that this angle here and this angle are the same, right? So let's get the first thing. For reflection, theta is equal to theta prime. This is called the law of reflection. It's not too hard. You can see why, basically. You can imagine if the light was a ball, it came in, bounced off the wall, right? Then angle in, angle out, right? It's not too hard. Okay. For refraction, turns out, obeys this, something like this. So this is material 1, material 2 has some index refraction N1. This has index refraction N2. All right, so vacuum N1 would be 1. So in this case, basically this is N1 sine of theta, I'll call it theta 1 now, theta 1 is equal to N2 sine of theta 2. I'll call this equal to theta 2, say. All right? Okay? And this is called Snell's law of refraction. Okay? Now you can also get this from the principle of least time, all right? Okay? Now how will you do that? Okay? So it turns out that you got to remember that light travels differently in these two places, right? Light travels differently than here, okay? So if you imagine that, let's say let's say you're on the beach, right? This is sand. Okay, so it's land. Actually, let's make it land. And this is water. All right? And the thing is that, like, you can imagine yourself here. Okay? And let's imagine you're a hero here, so I'll give you a cape. Okay? Now, you as a hero have seen someone out here. Okay? And they're struggling, right? They're not doing too well. Maybe there's a shark in the water, say, for instance. Okay? Maybe there's a big tidal wave coming. Okay? Anyway, this person needs help, right? And the thing is that you want to get from here to here as quickly as possible. Now, if this was all land, then you would know the way to get there is to basically run in a straight line and get there. But it's not land and water, right? It's land. It's not land and land. It's land and water, right? And you swim a lot slower than you can run. Okay, so you can imagine that. Okay, suppose I go here, I run down this way, and then I swim. Well, the problem with this is that, like, I'm swimming a long way. That's going to take a while for me to get this person. I won't get there as soon as possible. The other possibility, I could basically run this way and then swim across. Now that minimizes the time I take to swim. All right. And so if you swim really slow, this might be the right thing to do, right? But if the speed that you run land and the speed you swim water are not that different from each other, all right? But they are different, right? Then there's a middle ground where basically the optimal path is something like this, okay? Right? So you can imagine that here's just your angle theta. This is your angle theta 1, angle theta 2, right? This is N1, N2, right? So you can imagine that we want the optimal solution is something like V, right? It's actually sine theta 1 over V1 is equal to sine theta 2 over V2, right? If you hit it with a C here and a C here, this is N1 sine theta 1 equals N2 sine theta 2, right? This basically returns back Snell's law of refraction, right? So the problem of basically rescuing someone in the water and the problem of light traveling through two different materials are exactly the same problem, okay? Obeying the same thing. You want to minimize the time. So light knows about minimizing time, right? Which is interesting. Okay, so let's consider an example of this. Okay, not this example anymore, but a more prosaic example. So let's consider ray of light incident at 45 degrees, right? Okay. What is the angle of refraction for, okay, A, air and water, B, water and glass, and then C, diamond and air. Okay, so we'll consider the three possible examples, right? So let's draw a picture of this first. There it is. This is coming at 45 degrees. Draw the normal here. This is 45 degrees, right? Okay, and this is N1, N2, and then there's some angle here. Theta 2, which I do not know, and 45 degrees equals theta 1. Right, so I have that set up there, okay? So let's do part A then, okay? Air and water, okay? N1 sine theta 1 equals N2 sine theta 2, right? Simple enough, right? So let's see, air was 1 sine 45 is equal to, water was 1.3 sine theta 2. Okay, go ahead and compute this. Turns out to be theta 2 is equal to 32.1 degrees. Right? Simple enough. All right. B, okay? Let's do it again. N1 sine theta 1 equals N2, right? Sine theta 2, right? This is water and glass, so let's try to do this again. It's about 1.3 sine of 45, right? So this is water here. It's equal to N2, which is glass 1.5 sine theta 2, right? You basically work this thing out. This turns out to give you basically that theta 2 is about 39 degrees, right? Simple enough, right? So this thing comes in, it comes out at a steeper angle than it came in at. Okay. C, okay. Let's do diamond and air, right? So this is N1 sine theta 1 equals N2 sine theta 2, right? And that's where we're going to get something surprising here, right? So this is 2.4 sine of 45 is equal to air 1 sine of theta 2. Now here you get something interesting. 2.5 times 45 degrees, sine of 45 is gives by 0.707 or so, okay? This gives me 1.7 equal to sine theta 2. But sine can only be between 0 and minus 1 and 1. 1.7 is much bigger than 1. So in fact, there is no solution here. So what's up with this, right? I mean, like, diamond and air are interfaces that happen, right? Anytime, like, someone has a wedding ring on, or that's basically a diamond and air, okay? Okay, So what that means is that what this implies is that for some boundaries, which is basically comes from basically n1 bigger than n2, and some angles, theta 1, there is no solution. So what that means that is that there's no solution implies there's no refraction, all reflection. Okay? So this is known as total internal reflection. Okay? And so, the way to determine this thing is that you can imagine that as I increase this thing, eventually what happens is that I can get to the point where this thing points theta 2 essentially let me just try this right. I can basically keep doing this, right? So usually it's coming from a higher n1 than n2. I keep doing it too. Basically, it goes along here. So theta 2 is at 90 degrees, and beyond that point, nothing can be reflected, right? So this occurs when theta 2 equals 90, okay? Right? And so you get the minimum one, n1 sine of theta min is equal to n2 sine of 90, implies that sine theta min is equal to n2 over n1, right? Okay. Okay, so what does that mean, right? So for diamond and air, n1 equals 2.4, that's diamond, n2 is air, that's just 1, right? Sine theta min is equal to 1 over 2.4, which implies that theta min is equal to 24.6 degrees, right? So what that means is if this angle here is bigger than about 25 degrees for diamond, basically all the light is reflected inside the diamond and none of it comes out, right? Okay. Okay, so all angles theta greater than theta min, theta 1 greater than theta min, is basically total internal reflection. Okay. Right. Okay. Right. So we can also compute this angle. So this part's the reason why. So diamonds has the smallest angle for internal reflection, which is why diamonds sparkle actually. So if you hold a diamond, right, and you turn it, only certain angles will light escape from the from a certain facet, which is why they sparkle actually. So if you turn it and you turn it slightly away, that facet of the diamond which was sparkling basically no longer is sparkling anymore, no longer is transmitting light, which is why they sparkle so much. Right? Okay. All right. So just work it out, close out. So minimum angle for water sine theta min is equal to n2 over n1. That's 1 over 1.33. That gives you theta min about 49 degrees or so. All right. Okay. So that's like one part of the properties of light. Okay. Now we're going to talk about more properties of light. Okay. Let's talk a little bit about dispersion. Right. Okay. So the first thing to note is that the index of refraction, index of refraction, n depends on the wavelength of light. So the index of refraction, what does that really mean? It's basically the ratio between the speed of light and the speed of light in material in the speed of light in that material. And so if the index of refraction changes for different wavelengths, that means the speed of light changes for different colors, right? So that means the speed of light is different for different colors. Colors in material. Okay, that's interesting, right? Okay. Right. And so generally, okay, n is larger for shorter wavelengths. Okay? So this is bluer. The bluer you are, the larger the index of refraction, which means the smaller the speed of light is, right? So slower. Okay. All right, so let's imagine they have a situation of this. Let's consider a triangle here. Okay. So now you have some light being come in, right? It has some angle relative to the normal, right? If you have red light, it might bend this way, and then come out this way, it'll come out again this way, like that. Okay. You have blue light, it might bend a little more sharply here, and again, it'll do a little sharper down here. So this is basically red. This is blue, right? And you put it right here on some screen here. You get a layer of red and layer of blue, right? So red here and blue there, okay? And all the colors in between, basically. So this basically forms a rainbow, right? Or spectrum to be more precise, right? Okay, so armed with Snell's law, okay, you can actually go ahead and compute out basically why rainbows form, right? So we're going to do that right now, okay? So, okay, so what are rainbows? Rainbows, okay, result from dispersion, okay, which is just basically refraction. Refraction and internal reflection in spherical raindrops. Now you might wonder, I thought raindrops look like this. They don't actually. If you actually watch them in there, you freeze them in camera, they're actually almost nearly perfect balls. All right. So this actually turns out not to be a really excellent approximation. Okay. Okay. So to do this, right, we just have to draw a picture. Let me think about how to do this. Right. We'll draw a picture of a raindrop here. So let me draw a picture of a raindrop. It's a big circle here, right? So just draw a big circle there. Hopefully this is large enough to encompass everything you need to do. Okay, and there's going to be some sun here, right? And the observer is going to sit right about here, actually. I hope this is right. I never get this quite correct. So the sun shines on the raindrop. Okay. Let's go ahead and draw the normal right there. That's the normal. Okay. And this is going to be theta 1, say. All right. I'll write this theta 1. Okay. All right. And now continue this normal inward a little bit. Right. So let me just make sure this is correct. So I'm going to draw this thing symmetrically. I have to use a ruler. I use a ruler to do this because I'm going to screw it up otherwise. Good. I should do it roughly symmetrical. Okay. 1. Okay. It's going to be symmetrical again. So I'm going to draw it to the eyeball here. This is again normal. It doesn't look quite normal, but it is actually in fact normal. Okay. All right. And so I'm going to draw the light coming in like this. Yeah, I messed it up already. I can tell. I messed it up already. It's okay. All right. So it's fine. It's not the end of the world. Okay. So let me make sure I get this correct. Whoops, I screwed up. Okay, let's redraw it. Okay. I always mess it up. Okay, let me just redraw everything. Okay, let me just redraw it. Okay, it's not. Okay, so let's get the sun here again. Okay. All right, let's draw the perfect circle, as perfect as we can. Okay. I forgot to, here comes the sun, here comes the sun. Okay, so now, you gotta remember, I always forget, the normal in the spherical is actually goes through the center. That's key ingredient I forgot. Okay, there we go. Okay, so this angle here is theta 1, right? Beautiful. And now this thing will refract. Let me just draw this symmetry axis because we're going to need that later on. Okay. It's going to refract here. Okay. So this is now theta 2. And if we want to continue this thing, okay, this angle here is theta 1. Okay? All right? Now, it's going to reflect off this thing right here, all right? And it's going to come back. Okay? And let's draw this angle as well. Okay. All right. Okay, so these are all, I think these are all angles I need. Okay. Right. So it's a sphere. It's a sphere. Okay. And so this length and this length, or this is center, this length are the same, so this is the same length as this length, all right? Which means that these two angles are the same too, theta 2. Now, this is just a reflection here, so angle in equals angle out, so that's theta 2 as well, okay? And because this again is a triangle, not equilateral triangle, but a triangle with the same length sides here and here, that means this angle is also theta 2 as well, right? Okay. And then finally, because this is Snell's law here, right? N1 theta 1, N1 sine of theta 1 equals N2 sine of theta 2, right? So this is true here, that's the relation between that. Guess what? This here is, in this case, this is 1. N1 sine of theta 2 now, this is the 1 part here, is equal to, well, this is N2 now, is equal to N1 sine of theta 1, all right? These two are the same equation, that means this theta 1 is the same. This angle right here is theta 1 again, all right? Okay. Okay, so we have that. Now I want to be careful about this, all right? Okay, so what we're going to see, all right, so I should draw theta 1 to be slightly, yeah, I should draw theta 1 to be slightly less crazy. Okay, so theta 1, I didn't quite do that right. Let's make it a little bit more angle there. There we go, perfect, okay. All right, so if you continue this onward, right, so if you're observing it here, that's your eyeball, you can look, you can see the light coming in a straight line from somewhere over here, okay? We'll just exaggerate just a little bit just to make sure everything bends correctly. Right, okay, so somewhere over here, you will intercept everything, okay? And this angle here, which I want to try to understand, I'll call this, whoops, it's not quite right. This angle here is beta, and so this angle here is 2 beta, right? All right, so let's go ahead and try to figure out what all these angles are, right? Okay, so this entire angle up to here is theta 1, okay? Right, so there are several angles here, so let me just get this right. Let's see, so we'll call this angle here alpha, okay? So the triangle, so the sum of all triangles, the sum of all angles of the triangle adds up 180 degrees. So the first one is that I'm going to look this triangle, this one, and that one. So that means that 180 is equal to alpha plus beta plus theta 1. Okay, so that's the first angle right here. So it's this angle, this one, and that. Okay. Now the other angle I want to get is this alpha here. So this alpha is basically this angle and this angle, so theta, the 2 theta 2. So basically alpha plus 2 theta 2, that's also equal to 180 degrees or so, right? So those are my 2 angles here, right? So with this, like what I see is this angle beta, so I want to compute what that beta is, right? So the beta here is going to be equal to, let's go work this thing out. Right, so that's alpha. Alpha equals 180 minus 2 theta 2. Plug into that one, right? Okay, so it's 180 equals 180 minus 2 theta 1 plus beta plus theta 1, theta 2, sorry. Okay, and so this gives me that beta is equal to, right, 2 theta 2 minus theta 1, right? Okay, and I know what theta 2 was going to be, so beta is equal to 2, the inverse sine of basically n1 over n2 sine theta 1, right, minus theta 1, okay? So where did this piece come from? You remember that n1 sine theta 1 equals n2 sine theta 2, applies to sine theta 2 equals n2 over n1 sine theta 1, which implies that theta 2 is equal to sine minus 1, n2 over n1 sine theta 1. Okay? Right? So that's just that. Okay, so this is the thing I want to plot now, right? Okay? And the thing is that I can go ahead and let me just think about how to do this. I can go ahead and just compute this thing out. So I can just plug in some numbers. So I'm plugging some numbers. So theta 1 here. I'll write betas down here as well. Okay, let's plug in some numbers. All right. Okay, so let's see. I'll try 0, 10, 20, 30, 40, 50, 60, 70, 80, and 90. Okay, so we just get to that. There's my angle. All right, so I pre-computed this thing. I'll just go ahead and write the numbers down. 0, 5, 9.8, 14.16, 17.8. All right, 20.3, 21.3, 19.9, 15.5, and 7.5 or so. Okay. All right. And so, if you plot this thing out, theta 1 as beta, right? It starts out small, it gets to something big, peaks up, and it falls back down, right? And where's that peak? That peak's around 60 degrees or so. Okay? And basically, so beta is maximum, near 60 degrees, right? Which gives me a beta around 21 degrees or so, right? Which implies that 2 beta, which by C is 42 degrees or so, right? Okay. So what happens? Light can come from a variety of different angles, right? But because all the betas tend to be clustered around here, all right? That means that light from a number of angles all gets focused around basically about 21 degrees, which means 2 beta is about 42 degrees or so. Okay. So if you look at it in terms of geometrically, what that means, right? Here's the sun. There's some rain going on over here, right? There's an angle that you're going to see coming back, right? This angle is 42 degrees or so, right? Okay, and then you are here observing it, right? Which means that if you look at the sun's behind you, so it's just one way through. So basically, this way to sun, right? Okay, so these are parallel lines. This is also 42 degrees or so, right? Okay. So that means that basically you see a rainbow at an angle of 42 degrees from the sun axis, right? So there's some straight line pointing at the sun that points behind you. The angle you see the rainbow at is 42 degrees relative to that sun, right? So that's pretty cool, right? So next time you know how to look at the rainbow, right? So the rainbow, so it has to be behind you, and it has to be 42 degrees relative to basically what the sun direction is shining in, right? Okay, so let's talk about a few other things, all right? Let's talk a little about polarization. All right. Okay. So we discussed this before. Light is a transverse wave, right? So that the E field is along one of the transverse directions. What's the transverse direction? So basically light's moving along this way. The E field can be in this way or this way, okay? So basically direction for E field. Okay, this is the direction of light. Okay, so because of that, basically, that means that there's a polarization. So basically, I have light that's moving like that, or you have light that's moving like this. Okay, right. Okay, so the way you think about that is that you have, so if light is only along one of the transverse directions, there's only two, right? That means the light is linearly polarized. Right? Okay, so usually light is in both directions, right? There's components of light which is in say the y direction, components of y in the z direction, but sometimes if it's only in the x and the y direction, then it's considered to be linearly polarized, right? So basically that means that the E field, if it's linearly polarized, it's going to equal to E cosine of, let's say it's kz minus omega t along the x-axis, or E cosine kz minus omega t along the y-hat direction, right? But like not combination of the two. Okay. All right. So polarization can happen in multiple ways. So there's many ways to get polarization. Okay. This includes absorption, reflection, and scattering. Okay, we're going to go through each of these in turn. Well, don't go through each of these. We just describe them in turn. Right. Okay. Now, what we commonly deal with, all right, is usually we deal with basically absorption, and reflection. Okay, that's what we're used to think about in terms of polarization. Like, what do I mean by that? Sunglasses, polarized sunglasses work by absorption. They absorb certain transverse directions, but not other transverse directions. They're needed basically because basically if you're out in the near the water, okay, and the sunlight reflects in the water at a reasonable angle, the reflected light takes on the properties of the surface of the water, and so the surface of water tends to reflect certain certain directions better than others. And so reflection off the water can basically result in polarized light as well. Okay? The last thing is actually scattering can also absorb as well. Now you may not think about scattering too much, but every time you look up at the sky, and the blue sky, that light that you see is polarized, right? You can test it by if you look up at the sky on a blue sky day with your sunglasses, and you turn them basically 90 degrees or so, you can see more light and less light coming through. Okay, it's a pretty striking effect actually. Right. Okay, so what I say? Yes. Okay. So I'm going to look at for this stuff. I'm just looking at polarization by absorption, right? But all three polarizations are something that affects us on our day-to-day lives. Okay, so let's look at polarization by absorption. Okay, so if you imagine you have a polarized light like this, right? What you would get is that if you put a polarized filter across it, that, okay, nothing comes through, okay? So no transverse wave, so no transmission, right? Because the filters they're all in the wrong direction. On the other hand, if you have a light like this, and you put a polarization filter this way, then there's plenty of transmission, okay? 100% transmission. It's not 100%, right? Like, but it's much higher, okay, for absorption processes, right? It's just basically imperfection in manufacturing, repurposed material, or something like that, okay? Now, let's imagine you do something a little different. Let's imagine you have a polarized light like this, okay? And now, what you're going to do is you're going to hit it. So this is going to be some, I'll write this, E vector is equal to E0 cosine kz minus omega t in the y hat direction, right? And what I'm going to hit it with is, I'm not going to hit it with a vertical, I'm going to hit it with something which is at an angle, right? So this is a 45 degree polarizer. Okay. So in this case, basically, the component which is along this direction is just basically the cosine of 45 degrees, right? So what's transmitted is basically you have light that's at 45 degrees, right? So this light now transmitted is basically E is equal to E0 cosine kz minus omega t. Now there's two components now. There's going to be a cosine 45 in the y hat direction plus sine of 45 in the x hat direction. So you have these two components now, right? So now, if you hit it again, sorry, I made a mistake. So it's the 45 degrees here, and then there's only a fraction of this is in direction, which is again another cosine 45 again. Yeah, it's confusing, but okay, it's fine. Okay, good. All right. So now, if you hit it again, let's put it through another filter. So I'll call this basically situation 1. Situation 2, I'll call this E2 now. And now situation 3, I'm going to hit again with a vertical polarizer again. So I'm going to come through, and now only one part of this thing is actually along that direction, right? So this gets reduced down furthermore. Okay. So basically E3 is equal to now I just get this piece right here. E0 cosine kz minus omega t. Now it's cosine 45 times cosine 45 squared y hat. Okay, so that's the only piece that's left, right? Okay, so this is the E3, this is basically number 3 now. So we ask myself, what's the intensity of the transmission? Right, well that's substantially a lot less, right? So basically, I is basically equal to E squared now. And so, what that means is that I transmitted is equal to, so it could be E0 squared cosine 45 to the 4th power, right? And E0 squared is just the initial amount of intensity that I have, which I start out with, times cosine 45 squared, right? Okay, and so for any arbitrary angle, that means IT is equal to I0 cosine theta to the 4th power. Okay, and so this is called hold on, confused. Confused with one thing. Right, okay. So, for any arbitrary, for 2 filters, 2 polarizers. Okay, so for number 2, okay, so after 1 polarizer, IT for number 2 is equal to I0, and now there's only one 45 degree there. That's just cosine squared theta, okay? Now this is called the law of Malus, okay? So this one just comes from the fact that basically after this first filter, you use the law of Malus twice, you get a cosine to the 4th then, in that case, right? Okay. What do I want to say here? All right, so the last thing I want to talk a little bit about is Rayleigh scattering. Okay, so always very cool. All right, so what's Rayleigh scattering? So basically, tiny particles which are smaller than wavelength of light scatter light but amount of scattering goes like lambda to the minus 4, right? So what that implies is that long wavelengths, which is redder light, scatter less. Okay, so it's pretty remarkable. It's like basically if you have very, very small parts, smaller than the size of the light that you're trying to scatter, they will still scatter light, right? And they scatter it depending on the wavelength, okay? Then short wavelength. Blue. Okay. And so basically, if you imagine that there's a sun here, and this is the entire atmosphere of the Earth, and you're underneath this atmosphere, okay? The sun shines on everything, okay? What happens is that as it passes through water vapor in the air, the water vapor particles actually scatter blue light, preferentially than red light. Okay? So this is basic blue scatter. Okay? And if you're on the other side of the world, where you see sunset, we see it's red light here, okay? And so when you are here, like high noon or something, the sun's kind of above you, right? You look up, basically, you see all the blue being scattered by the sun. That's basically the blue sky. And then if you're late in the evening, you're looking through all that atmosphere scattering away all that blue. You see red light. This gives you a red sunset, right? So basically, rarely scattering, so this is basically why. Sky blue, and sunsets are red. So next time someone asks you, basically, why is the sky blue? You tell them, well, because sunsets are red, right? As if basically that was the obvious thing to say. Okay, great. So that's basically it. There is technically one more lecture, but that lecture won't be on the exam, and it cannot be tested either because there's no problem set for it. So I may skip it, right? And we will just probably go to exam review.